Yeah. So, hello everyone. I've just paused the recording for a moment. So today there's the first session regarding FEMM. First session from Curious Qubit blog. So the first session we have planned was a hands-on session with FEMM software. So I've made a presentation for that. I will just start with that. So the session is Demystifying Electromagnetic Simulations, a hand-on session with FEMM. So basically what we are going to learn, what are the contents we will cover in this session are like on the slide. And don't just get bothered with this information on this. It is a very simple, and we are not going to go into the very depths of electromagnetics, not on the physics and engineering side. We are going to more deal with the simulation thing, which requires more of hands-on experience and more of practice. But it is true that we have to know some theoretical knowledge to understand what's happening and what's wrong with the complete model. But now we are not going to deal with the calculations in math. So the first topic is, what are the terms magnet and magnetic? We have used the words magnet and magnetic. So basically, in very simple terms, not talking about the physics behind what is a magnet, which deals with the intrinsic spins and everything of at atomic level. So we are dealing with a very simple terms, which is anything which attracts iron is a magnet. This definition is wrong, I know, but to understand it's very simple. I'm pretty damn sure everyone have seen this kind of magnets or this kind of magnets in lab or in a old speaker. Possibly someone would have damaged those. I think everyone does that. So magnets are a very important part in our life. They're playing a very, very important part in our life. At least in this time. In 2025 there are almost around hundreds of magnets around us which we don't know. The typical first example I would give is a mobile phone. It has a speaker, it has got a magnet, it has got a mic, it has got a magnet. And the laptop which you're using has a speaker, a TV has a speaker, and apart from these things, there are magnets in pretty much everything. You can take a BLDC fan, which is the modern fan which is being used. It's a BLDC fan, so that has a magnet, and the EVs have magnets, and they're pretty much everywhere. So anything which attracts iron is a magnet for now. So what is magnetic then? Anything which is attracted by a magnet is a magnetic material, or it's called magnetic. So and the other note is not all magnetic materials are iron, because iron is also attracted to magnet, and there are many other things which get attracted to magnet. So iron is magnetic, nickel is magnetic, iron is magnetic, and cobalt is magnetic. So we have got magnetic materials. And for example, understanding what is a magnet, we just use the intuitive understanding, because we are familiar with something getting attracted to magnet, which is iron in our daily life, in our childhood. So that is what I've meant here. So what are circuits? That is the second question. What are circuits? So circuits are very simple, fairly. This is just a circuit consisting of a battery, a bulb, and a switch, which is typically equivalent to a switch and a bulb or a fan in your house. So this is represented in this way, wherein we can use mathematics to solve this. It's much easier and much simpler to understand, because see, you can have a different type of switch, you can have a different type of bulb, you can have a different size of battery, but you can't draw this kind of circuit every time to calculate. So it's much simpler to represent them with symbols and just use values. So this is almost an equivalent, where everything which you have to calculate, you just do with the formula. So coming to the next part, what are magnetic circuits? So everyone is familiar with this electric circuits. But what are these magnetic circuits? Maybe not everyone is familiar, but If people are attending this session, I'm damn sure they know what a magnetic circuit is, but for just a brief intro about it. Yeah, so now we'll just see what are these two components and then answer. These two are inductors. I'm pretty damn sure that every electronics engineer who has worked on a PCB should know what this is. So this is an inductor. This is also an inductor. This a toroidal inductor, and this is a shell type inductor, which mainly the names come from the shape of the core. This is called the core, and here this is the magnetic material, which is ferrite, which means some material which is related to ferromagnetic substances. You can know more about magnetic substances if you are having some questions on it. You can just search about them, but for now we are skipping that topic. So these things are pretty important in an electronic circuit, because in RF circuits or in filter circuits or in power electronic circuits as a filter, or even for resonators and many other things, we need inductance or inductors or these kind of things. So okay, so this is an inductor, but we can't always build an inductor, because let us first suppose example, let us assume we need some 10 microhenry inductor. We can't make it and find it's not 10 Henry and go change it and then move to a different size, different shape, and then search it. So that's not possible. So what we do is modular circuit and solve it. So this circuit is an equivalent of it. So if you observe, these coils are modeled here and these paths are modeled here. So these coil and the current flows, as we know, as you are here, produce an Ni, which is an electrical equivalent of voltage. So it is put here, and the path here is identical to what we have seen here. See, there is a wire where current is flowing. So this is a path where flux is flowing, and then this is the reluctance, which is equivalent to the resistance offered by this tungsten filament. So this is reluctance. So that is put with R. There is some reluctance here, the reluctance here, and reluctance here. So there are three. So these are the phi is the flux which is equivalent to current. So this is a simple magnetic circuit. So I am taking this as an example. We just understood it already, what this actually means. And here the calculations and all the values are to be done with these formula. We calculate the resistance, the reluctance, and we just put it. So S and R are not different; they are interchangeably used everywhere. So they both are the same. And mu is the permeability. So we are assuming that the core is infinitely permeable for this calculation, and we do calculate. But in real life, we know that the permeability is not infinity. Surely there will be different permeability based upon different saturations, different flux densities. As you know, a core is nonlinear, iron is nonlinear, they have saturation points, knee points and all. So what we cannot do is, we don't know where the saturation will be high, where the saturation will be low, so we cannot do the calculation. So ideally what we do is, we put it to infinity or some value like 10,000, 15,000, which is approximately equal. That is what we assume, and then do the calculations. But how accurate are these calculations? How accurate can we do with the analytical calculations? I am pretty sure we cannot. For this fairly simple structure, maybe we can, but for a complex structure, if the inductor is like, let us first suppose assume having some complex shape, maybe it is just going this way, maybe like a circle, or going like a wobbly thing. I mean, jiggly thing. We cannot do that. So that will be fairly tough because we don't know the saturations. So that is very difficult. And also practicality. The other thing comes is like, if we change this distance, okay, now we are assuming that all the flux flowing through this flowing through this limb, jumps this air gap and goes through this. But what if we increase the distance? What if increase the distance further? Does the flux really go straight? Because it also has, it can take this path, it can take this path, and also it can just jump this way, and also it can just jump this way, jump this way. So why should it go straight? So it doesn't. It will surely not. So being practical, we cannot analytically calculate everything. That is difficult and time consuming. Not every time efficient. So what we need is a FEMM software, a finite element software. There is one software, FEMM. It's an open source tool. It's one of the best tools I have ever used in an open source community. And very thanks to David Meeker. Sorry if I'm pronouncing it wrong, but this software is a wonderful software. It helps, like, it really helps many students in the industry and many industrial professionals, academia, and yeah, lot. FEMM, this is a wonderful tool, and you can just know more about him on this link, and you can download FEMM software on this link and this icon. So coming to FEMM modeling, so basically this inductor is drawn like this, and it is modeled like this in FEMM. So we'll first understand how we have come up with this structure here. Okay, so yeah, so take my setup. So I already have a model, but yeah, I'll make a new model. I thought it would work. Okay, give me a minute. So yeah, if you search FEMM in your start after installing through that link, this window pops. It really looks like a Windows XP version, but believe me, that was the same thing I felt when I opened it first. But it is a wonderful software. Just click it. Just click. There are many problems which you can solve, but we are dealing with magnetic problem. And just click OK. So you get an interface, and now we have to understand. So if you see this is an inductor, and you see it has, let us assume depth is 2 mm, and the width is 5 and 5, total 10, and this is total 10, and there is an air gap of 0.1. So these are the dimensions I am assuming. Okay. So yeah, let us see what. So there are many options, and pretty much like file is the same for every software, and these are some we'll see. Yeah, so the first main thing is problem. So let us stick to planar for this discussion, and it is fairly simple, and we are talking in mm. So yeah, mm. And the frequency, we wanted to design an inductor. Yeah, so we'll start with 0 Hertz, and you can explore more putting different frequencies and all, but let us start with DC current. DC is 0 Hertz, so I'm starting with DC current. And then there is depth. Depth is 2 mm. That is what we have seen here. See, it is 2 mm in depth. So yeah, 2 mm. And these all are for your what do you say? You can just explore. These are all for your exploration. So we'll start with the depth. I'm putting 2, which is 2 mm, which we have discussed. And also, yeah. And now we have to draw this geometry over here. So first we'll start with this geometry, and then we can understand about these rings and all. Yeah. So fairly, these are the different features here. So we'll start with the point. So in order to draw lines, okay, you can draw a line by selecting line, like yeah, many other tools do, but no, you can't do it here. So you have to draw points and then lines. So yeah, you have to go on the bottom left. If you see, you can see the coordinate. Go and select the coordinate where you want, and then there is a point, but tough. So this is not an ideal way to do. What we can do is click the point and then press tab. There you can enter the coordinate. So what have we discussed? We wanted this extreme point to be 5. Okay, 0 and 5, and then we wanted the height from 0 to be 5, so it will be minus 5 comma 5. So yeah, minus 5 and 5. If you press home, you can see the point somewhere. You have to zoom in and zoom out to get there, so you can just use these tools. Yeah, so yeah, we found our point. We'll zoom in near that point. Okay, and then there are other points which we have to add. We'll add as 5, 0 and 5. Okay, and then we also need one more point here. We'll add that later. And also one more things we have to assume are the thickness of these limbs are same. This is 2, and assume this is also 2, this is also 2. Okay, so it will be, this point would be 2 mm right and 2 mm down from this point, right? So what you can do is actually copy the point. This option is for copy. So 2 mm to the right is positive 2, and 2 mm to the down is negative 2. You've got the point. And also, yeah, see, by mistake I've added a point. So what you tell is you can just do Control Z and undo everything, right? So I'm just trying that. You'll know what happens. See, fairly one has gone. If I'll press undo again, means Control Z, this point also should go away, right? Ideally. No, it returns back. FEMM is only having undo for once, only for the last step. Okay, so if you just spoil your operations and you do something which is wrong, you cannot undo it. So yeah, go select it, select vertical shift -2m. Okay, pretty straightforward. And then select line, and then select the point you want to join. So it takes shape, and now we wanted to select this thing, and also it is the same thing. It will be replicating here over the x-axis. It's just a mirror symmetry, so there is an option for that very easily. This for selecting all. So yeah, I'll show that also. See, if you're selecting this point and right clicking, it gets selected. Okay, but if you're selecting a line and select it, it's not getting selected. So basically try to use all. If you wanted to select many things, you'll get to know why I'm selecting all, but yeah, for now just believe me. So I selected everything. Not a copy, we need a mirror image. So mirror image, and we have to define the point of symmetry. So mine is x-axis, so done. And also I need an air gap here, which is -5 and 0.1 mm in height, which means 0.1 by 2, half on the both the sides, above and below. I would have done this before, I just forgot. It's not like we have to do it this way. Horizontal shift is 2. I'm just applying the same. Yeah, see. Let's zoom in over here. We can see the air gap. We can also measure. I'll show you how to measure. So draw line and right click it, it's getting selected. If you are doing double tap, you can see the dimensions. So here if you see, it's 0.1 mm. That's what we wanted. So I'm just deleting that line. So, and now I wanted to replicate this over this side. Okay, we forgot about the center limb. Center limb is also 2 mm width. So it means this, if you see, this is at 0, right? It's at 0, 0,3. We don't want that. We actually need it at 1. X should be -1. This point should be at -1. I have made a mistake. So what we can do, we can just use the tool move, -1. right? And maybe I'll just delete this point. I'll tell why. Don't make me don't get angry on me because I'm just doing few mistakes. Like I don't basically use this tool. FEMM has an integration with MATLAB and Python, so that's also one more advantage. That is for other session, the MATLAB thing, but yeah, I just told you. You can see it taking shape. See, everything is done. But here I haven't added any lines, but here I'm gonna add some lines. I'll show you why. I'll tell you why after some time. So we are able to successfully build an equivalent similar model. See, right? Yeah. So everything is done, but where are the coils? If you see, there is a coil over here, but where are the coils here? So you need to define something. So I can't draw a coil here. So what I would do, I would rather take a small section and show. Let us think the coil has some thickness. It is let us assume it is 0.1 mm in width or thickness, whatever you call. So I just copied the points and then just replicating this on the other side. See, I've done. So, but where are the number of turns? I assumed, okay, well, let us assume there are 10 number of turns. But how will you do the 10 number of turns? I don't want to cut everything and make a big big mess. So what I can do, I'll show you. Wait. So until then we'll go. Yeah. So let us assume this is the 10 turns coil. I'll tell you what will happen and how we'll do it. So for now, yeah, you have completed geometry. Everything is done. But how will the software get to know that this is iron or this is the core, this is the coil which is typically copper, and this is air around it? How will it know? It doesn't. How will it know? It cannot. So let us see what we have. There's properties and there are materials, and we'll add a property. We'll add with some name air. Linear, air is linear material, and yeah, okay. And we need another one which is core linear relationship. You are assuming 10,000 linear for now. 10,000, okay. And then add property which is copper, which is basically copper doesn't get attracted to magnet, so it is almost like air in magnetic properties, and the conductivity of this is 58 megasiemens per meter. Okay, so there are three materials which we need, but how will I assign? There's an option here with a green circle, green dot inside. Okay, there are two circles, sorry. So yeah, to assign a material to one particular part, we need that part to be enclosed. That is the reason I was closing all the parts, but I'll tell you why I was closing this. You will get to know once I'll zoom in. So yeah, core, air. Let us see. We'll zoom in. Yeah. Yeah, this is air. And see, I wanted to assign copper here. So if this is open, this hole will become a single material. So I cannot assign copper for this. That is the reason I was closing it. So yeah, so let us assign. So I'm selecting these air regions first, and then we have to press spacebar after selecting. Select all which you wanted to assign. You can do it one after another, but this is a group technique where you can select everything at once and press spacebar, and then here you get to assign the material. So I'm assigning air. Air is assigned, and I'm selecting these two, the core, assigned. This is copper. That's also assigned. Okay. So after this, how will I tell how much amount of current is flowing to copper? Okay, I didn't tell it. Let us see what will happen first with this one. So yeah, I'll show you the other thing. Before assigning elements, I would have shown other thing. Okay, but I forgot. But okay, we'll do that. We'll do that in the last. So there is something called copper, but we don't know how much current is there. Once we'll select this one, see there is one option with circuit. We'll see if it is also available for core. See, it's also available here. It's available, but okay, I thought it wouldn't be, but it's available. So select it and just see if there is some circuit. No, there is no circuit. So what we'll do, you see here, there is something called circuits. Add property, select, this is your new circuit, so circuit 1, then tell everything is in series. We'll talk about parallel later, you can just explore, we'll not talk about it in this session. So we'll think 10 amperes of current is flowing. So yeah, just select these two and click circuit, select circuit, and see, you can see 10 number of pins. Just assign. But if you see, both are positive. But how will it know the current is going in and going out? Because its coil is one side inwards and one side outwards. So positive number of turns are outward turns and the negative number of turns are inward turns. So you have to give a negative 10 here for correct results. Okay. So now we are pretty done with everything. I know the results will be wrong now also, but yeah, we'll see what is wrong and why. For now, all the materials are assigned. For a fairly simple calculation where you do this, these are all the sufficient information, right? So if you see, you have given 10 turns, and if you come 10 amperes, and then you have got a core, you have got air, and you have got copper. Wait, there is something. Air. Oh, okay. So yeah, we'll just do this. So you have to first save this. We'll save as a FEMM session project. I'll add this all onto a GitHub repo and I'll share that on your on the blog. So FEMM session. So it is saved, and now I'll show you one option. This is called mesh. See, there is everything got into pieces, but if you see, this air is not into pieces. Why? What are these pieces? First we'll understand, then you'll understand what happened here. So basically what it does is, iron core is made up of atoms, right? So when you are practically doing something, every atom aligns or arranges according to the Ni applied to establish a flux. But in this model, we lump all the parameters to make one single circuit and then do. But that is wrong, because every atom has to change. But we cannot put every small atom, and we can't do a simulation, because that is very a lot of calculation. There will be a lot of billions, trillions of atoms. So that is wrong. I mean, that cannot be done. So that is wrong. Which one? The circuit is wrong, and these atoms cannot be in. What we can do? We can actually make it into pieces and then solve for it. So it will be somewhere between the truth, which is atomic level, and somewhere between a little approximation, which is a circuit. So it is approximately equal to both, but a little efficient than a circuit, and approximately equals to the real scenario. Okay, so we have to break, but we have assigned air here, if you see. But if you wanted to break this region, if you observe, this air is flowing through this region. It's going out. Where is it ending? It's not ending. So the solver doesn't know where to solve, where to stop. So it's not understanding. So you have to have a boundary, a complete boundary. So there is also one more requirement, a reason for a boundary, but for now let's understand it this way. So there is one inherent option, which is an open boundary builder. Just click it, don't change anything, it's good like this. You can understand about this more, you can just search about it, understand it, and explore it. Always. Just click OK. See, it has done something for us. It has assigned some materials, it has assigned something else, but okay, it has done something. Now we'll see. See, now everything is done. But there is a catch now also. Let's zoom in. Okay, this mesh actually makes the system lag, so I'm just doing the purge mesh, which is not deleting the mesh, it's just hiding the mesh. So if you see, this air is connected and to this air through this outer surface. So we don't need two elements, but we'll see what will happen. We'll leave it for now. We'll see. So this is analyze option, which is a solver which solves all this stuff which you have done, like what we do here. We do some calculations. The same way it does some Maxwell's calculations behind. So we'll see. It did something, and this is the viewer. But see, some regions in the problem have been defined more than by one block level. These potential problematic regions will appear as selected in the initial view. Okay. See, air has got selected, which means there are two materials assigned. So even if they are air, same region, never do that mistake. Okay. So they are gonna delete it. Okay, we'll delete some or other air. I'm deleting this way. Okay. So it is done. And now we can click analyze and just view the solution. So there is no problem. Everything looks good. See, now if you see, the core and the flux, everything is visible, which you cannot do that in an analytical thing. So it is awesome. It's a wonderful thing. Okay. FEMM is a wonderful tool. I'll be honest. So yeah. So now with this, we will explore these options. We have already explored these options. We have explored point, line, and block. This is called a block. This is select for all. Yeah, this will be useful when you're selecting. You want to select everything and move it a bit or something. It will be useful. That is why I told a little last. So mesh, analyze, and view the solution. And this is the undo one. We are using Control Z. It's the undo. And this is for selection. And this is for circular selection, with selection this way. It's the same. So yeah, this for move, this for copy, and you can explore this for mirror, and this for the boundary. So we have explored all these tools now, and now we are exploring the tools in the answer. This is called a FEMM file, and this is an answer file. So if you see, there is a FEMM output window here. If you select this point and click here, you can see the flux densities B, A vector potential A, and H, magnitudes in the components, vector components, and the permeability. We have taken a linear core now, so everywhere the permeability is same, and yeah, everything, the energy and yeah, whatnot, energy density. Yeah, see, you can see. So this is a wonderful tool. So again, don't mind me telling wonderful tool these many times. So also we can see flux density plot, and also we can see flux vector plot. You'll understand what these are. Just give me a minute. this is the same plot which you draw. The flux is going this way. See, we have thought this is inside and this is outside. Sorry, this is outside and this is inside. Yeah, with Maxwell's corkscrew rule or right hand thumb rule, whatever you call, you can see that the flux goes towards the top. So yeah, it's matching, and also we can calculate analytically and see how close it is. And also one more observation which we can derive and we can just do without any calculation is that the thickness is same. So the for this one, so the reluctance would be same, and the flux flowing would exactly divide into half and flow this way. So you can see that also. So we just intuitively feel that. So it is 0.9 Tesla in the center limb. So it must be around 0.5. See, it's 0.5. I mean 0.45. If it's 0.93, it should be 0.45, right? Something around that. So it's wonderful. Can you see that? It's a wonderful thing. And now you can also do many things. I'll show you. So let's not show this plot for some time so that our rendering would be easier. And we'll just remove this also. None. Okay. And yeah, this is one thing. You can increase the number of flux lines. Yeah, we'll see. Wait. So we know that the flux lines just won't come straight. Sometimes this effect is called fringing. So if yeah, I'll put 50. You can see a very minimal fringing also. See, you can see perfect fringing there. Here also there is a little fringing. So you can see that if you put more lines. I'm just removing that also. So now what we are gonna see. Now we are gonna see the main thing, which is what we are doing it for an inductance. So there is an option coil here, like an inductor. Click that in circuit. If you see, you can see flux linkage, voltage drop, total current, and then comes flux by current, which is inductance, 3.784253 e power minus 6 henries. See that? So that is the amount of inductance which this setup is offering. And then we can also use the point. So now we'll use this line. So we can also see that. Select these lines. Okay. Instead of not getting confused between the FEMM and the answer file, I'll just put a plot. So I selected this line, and there is something called plot. I wanted the normal flux density, so the flux density was going this way. So we'll see how it shows. See, it is minus 0.4. Don't consider these edges, that is due to some other effects. But see that it is minus 0.4 Tesla. Got it? Because it is going towards the bottom. Just press escape to just deselect this line. Select this line. Plot. Normal flux density. Okay. See, it is also minus 0.4. That's what we thought this should be equal. And on the center limb, it should be double. Plot it. There are many other plots you can try. I'm just showing one. See, it's around 0.9. So it's almost double. So that is what we assumed. We can intuitively understand. So this is almost approximate to a real inductor with linear permeability of 10,000. Okay, we'll see what happens with non-linearity as well. So yeah, pretty much straightforward. And now we wanted to see what is the flux flowing through this. How will we do that? Flux is just an integral of flux density, right? Select these 2 points. There is an integral symbol here. Integral of Bn. Okay. See, it is 1.61 Webers, microwebers. So it must be 1.61 times 2, which would be 3.2, something around that. So we'll see. Okay, 3.4 micro. Okay, possible. That is possible because here there is a lot of fringing. So that could have accounted to that reduction here. So here it only has 1, but here if you see there are 2. So the flux density, the amount of fringing could be the same values. It might have lost some x value here and x value here. It became 2x, but here it is only lost 3x. Maybe I'm not sure, but something. But it is. I can believe it. I'll surely believe it. So yeah, we can calculate the flux. So we have calculated the flux. There is flux linkage. There is inductance. There is voltage, current, flux density, H, and everything, whatnot. Everything you need is available in this plots. So these are the operations. And then you don't actually need to take only these points. Basically what you can do is you can add any point like this. Wait, I'll show one. Yeah, I'll take it like this. You can just click tab, the same way. 5, no, I'll put it 0 and I'll put it 5. I'm taking it linearly like this. Sorry, I just got a message. So yeah, so continuing this, so yeah, we've got many parameters available here. Yeah, basically what should work, yeah, you can add a line point anywhere. See, basically you just select the line and you can press tab and add point anywhere, so that is possible. So you can get, wait, I'll add it here, tab, press tab. So okay, this is possible. This is what we assume. See, here the flux density is less because it is separated. Here it is high, and here it is a little reduced because there is also fringing accounted. Yeah, that's it. Pretty much everything. So just close this plot. And then now we'll see one more thing, which is a nonlinear core. We'll see that materials. There is material library where you have some materials. You can also add new materials as I showed. So we'll take one soft magnetic material with US steel, some steel with iron. So I wanted to use that. So already it has got added in the library. So I'm just using it here when I drag and drop. Okay. So we'll see how is if it is a nonlinear material. Use steel, modified property. See, this is not highlighted. Nonlinear BH curve, edit BH curve, plot BH curve. See, there is some linear zone here. Basically, you are not able to see because of this magnification. I'll see if we can. Okay, we cannot change that. Okay, fine. So it's a linear zone, a little linear zone. I will not tell perfectly linear, but this is a saturation zone. This is the most nonlinear zone after some H. Here the knee point is at 1.6 and it is having a saturation flux density of around 2. It is not exact, but I'm just approximately telling you. So I'm just using that material here in the simulation. So it is 2, but our flux density is 1. So I don't think we can properly see. So what I wanted to do is double the current to increase the flux densities, or triple the current. Yeah, okay, we'll do it double and triple the current. Okay, so first double, because earlier we were getting 1 Tesla, which means now doubling it should go to 2 Tesla, but we know that it is saturating, so it should not go, but we'll see. Yeah, earlier it just did it 1 iteration, but it's taking more iterations because it is non-linear. Yeah, and now the output window is not there here. It's gone, so we'll go to view and just set that output window. We got it back. It's 1.6 Tesla, it's not doubled. And if you see the permeability, it's 305. Here It is 9200. See, the permeability is reduced. Understand? And then we'll see with 30 amperes, which should be basically, if it's an ideal core, it should be scaled linearly, but it won't. We know that, but we're just trying. Okay, and then analyze. See, open output window. See, it is still 1.8 Tesla. It's not 3 Tesla. The permeability must have gone even lower. See, it's 98. It means the permeability is going low because it is getting saturated. But again, once we'll take up a linear material here. We'll take the same linear core which we have used. Core. Okay. And then analyze with 30 amperes. We should get 3 Tesla around. See, we're getting around 3 Tesla. Observe that here in the center limb, and here we must get 1.5. Yeah, 1.3. Perfect. So this tool is perfect for, I would not use the word perfect, but it is a good approximation for real life scenarios. So this is how you can analyze an existing inductor if you know the dimensions. If you wanted to design a inductor using this, what you must have to do is link it with Python or link it with MATLAB if you have license. Do some, actually it has some codings compatibility, so you can go through the documentation. Maybe we'll have a session on that if requested. So you can use genetic algorithms or gradient descent or Newton-Raphson or any algorithm if you prefer, whatever you prefer, and you can change this lens, change the material, change whatever you have. You have everything in hand, and maybe we'll discuss about this boundary conditions other time. There are many boundary conditions which are used in the motor design, periodic designs. So we'll discuss about them further upcoming days maybe. But for now, this is a perfect one. You can use MATLAB, you can use Python to actually do the optimization. Okay. So okay. So pretty small summary about all this what we have learned. So we have learned about different what is the difference between magnet and magnetic, what are those in circuits, magnetic circuits, and understanding simple circuits, and what do we do with analytical calculations, and what we have to consider in practicality, and what is FEMM and the greatness of FEMM. Yeah, I'm just obsessed with FEMM, and FEMM modeling, geometric modeling, and what is FEMM method, which is that breaking down of the component into small pieces and then analyzing it, and then the results. Okay, I'll just take 2 plots. I'll add those plots. I wanted you people to have that excitement, so I haven't added that plots in that presentation until you have seen that here. So I'll just add 2 plots maybe, because they'll be for your reference, and also with the lines I'll take some 3 lines. I'll remove this flux density. You can change the lower bound and upper bound to change the scale. So yeah, and also we'll add this arrow marks for B. Okay, we'll take this plot also. So yeah, this all about FEMM, the basics about FEMM. So yeah, I'll again tell. So about the finite element thing, the finite element method, and then the different tools which are point, line, block, select all, meshing, analysis, view analysis, undo, rectangular select, circular select, move, copy, mirror, and then the boundaries. I have left the scale. This is the scale option, you can go through it. And then the arc is nothing. If you need some arc circular thing, so here let us assume that the core is not this like this, it is like this, like a semicircle. So this 180 is for semicircle. So yeah, it is geometric tool. Okay, yeah, okay, if you are interested, I'll just press analyze so you can see some results. This. You'll see how it is. Even I don't know. It's all waste. Here there's no flux, everything is just going this way, so it's a waste. So this is what is optimization. So if you have something like this, the optimizer, if you do some Python scripting, optimizes that this is a waste of resource, so it will reduce it. Okay, so that is how we can use optimization. So then wait, I'll just click undo. Okay, undo is only once, I forgot. Just save, then analyze. Yeah, I'll add this into the repo. I'll add a repo, I'll share it with you all guys on my GitHub through the blog in the resources. I have recorded this session as well. I'll share a recording of this session also in the same blog on maybe I'll start one YouTube channel only for these sessions maybe, and I'll add them on that and share it on the blog. Okay, so yeah, in our time which we have thought, we were able to complete. So these are the tools, sorry again I forgot, these are the tools for FEMM and the answers. You have again the point, line, and this one you can explore. This is a graph, integral, and this is the circuit parameter. And then here also you can just see the mesh. That is not a big thing, so you can just off it. The flux lines and vector plot and the flux density plot. The same goes with these. These are the same things. Maximize, zoom out, selectively zoom, move. Yeah. And this is a scale. You can just compare it here. I don't think it will move. I'll just see. So no, it's not moving. So you can just move this and you can compare. Okay. Explore more, enjoy, try some new things, try some new components which are available with you, so that yeah, you'll get some hands-on experience. And this really helpful for see, for example, if you're a student and you're doing some project in your final year, and yeah, it is helpful. And if you're an industry person and you need some design for some new component, some inductor, some transformer or something, you can start with a basic design in this. And there are even a little more advanced things, such as there is steady state AC analysis when you put frequency, and then there is one more thing. Wait, I forgot. What? Yeah, this one. There is axisymmetric models for maybe what do you say? If the symmetry is around this axis, if there is one axis here and the symmetry, if there is symmetry on that around that axis, that is called axisymmetric. That elements also can be done. So you can explore. There is a lot to explore in FEMM. And yeah, again, I would like to thank David Meeker for all his support on FEMM. And yeah, so by this I'm concluding the session. Thank you.